Hello everyone, welcome to my channel. And from now on I've thought of starting a series of videos in which I will discuss some basic concepts of chemistry, concepts which are required right from class 11 12 to even if you want to pursue higher education in chemistry like B.Sc or M.Sc. And these concepts will be very essential if you aim to give competitive exams like JEE Advanced, NEET, or even JAM or NEET or GATE. So we will be study the concept in details, because I have seen in many cases people often just uh, memorize the formulas and they do not actually understand the concept clearly. So for them, as the thing gets tougher, it gets harder for them to actually understand the concepts. So first of all, we will start today with the concept of molar mass, formula mass and equivalent weight, which is present in the first chapter of class 11. So let us begin. First we will start with what is a mole. So what is a mole? First of all, we have to understand the mole is the unit of an amount of substance. In terms of chemistry, a substance is anything which is made up of some atoms or molecules, and which is basically what we usually call as matter. So anything like water, sand, air, everything is a substance. So first let us consider one molecule, ion or atom of a substance X. It can be anything. So we are considering here only pure substances which are made up of only one kind of atom, molecules or ions. So one molecule or atom we can see here. Now if we have 6.02 into 10 to the power 23 molecules, ions or atoms, which are called species, like 6.02 into 10 to the power 3 of any of them, like this number of molecules, this number of atoms, or this number of ions. And ions, it can be like in NaCl we have 2 ions, so total this number of both Na and Cl, like that. So if we have that amount of substance, we can call it 1 mole of that substance, and this number, it is a constant. It is known as the Avogadro's number or Avogadro's constant, which is represented by Na. Now we come to something called molecular mass and gram molecular mass, which is kind of a weird thing, because in books it is only written that whatever the molecular mass is, if we write the same thing in gram, it becomes gram molecular mass. So it can be sometimes difficult to understand. First we have to understand what molecular mass is. So for that we have to first understand AMU, or atomic mass unit. Now a mass of an atom is basically the mass of its protons and neutrons, which are the nucleons, because the electrons have negligible mass. So here we see the mass of one nucleon, which is the average of proton neutron, 1.66 into 10 to the power minus 27 kg, and that is called AMU. Now if we take the weight of the molecule, will be in the order of AMU. Like for hydrogen, it is almost exactly equal to 1 AMU, but there is some like 1.008 if we transfer it from AMU to gram. So how do we transfer from AMU to gram? Now this is the weight of one molecule, and we know that to get to a mole from a molecule, we need to multiply by Avogadro's number Na, which is 6.02 into 10 to the power 23. So this mass of a nucleon, which is 1.66 into 10 to the power minus 27, to multiply it by the Avogadro's number, and we get this one, 9.99 into 10 to the power minus 4 kg, which is almost equal to 1 gram. So now if we see like for water the mass in AMU will be 18, because oxygen it has a mass number 16 and two hydrogens it has a mass number 1 and 1, so it will be 18. Now if we want to find the weight of 1 mole of water, so again 1 molecule 1 mole, so we multiply by 6.02 and 10 to the power 23, so it will be this thing multiplied by 18, so we will get 18 gram. So here we had got 18 AMU and here we will get 18 gram. So it will just convert the unit from AMU to gram. We get the weight of 1 mole of a substance, and this weight of 1 mole of a substance is called gram molecular mass or gram atomic mass, because it is expressed in gram. And we can also simply call it molar mass, because it is the mass of 1 mole of the substance, and the unit will be gram per mole, because it is a weight in gram of 1 mole of a substance. So for water, as we earlier told, that it will be 18 gram per mole. So let us go to another thing called formula mass. As I was talking about NaCl. Like NaCl is an ionic solid, like Na and Cl, like you can say A and B. So in like molecule or any gas, like we were talking about water. So in water, if you have 1 mole of water, you will only have 1 mole of one kind of molecules. But here we see we have 2 kinds of ions. So here we don't have anything called molecules, because NaCl we usually write NaCl, but that is not actually how it stays in a solution. And even in solid, we have here we represent Na by the red and Cl by the blue. So like for here we are representing by AB. So like Na and Cl both are there, but there is no such thing as a single molecule called NaCl. So in such cases, the concept of molecular mass actually doesn't work. So we have to use the concept of formula mass. Because what is the problem? Like if in this beaker we had 1 mole of water and we halved it, like we poured the half of it into another beaker. So we had only water molecules here. So half of the water molecules will go here, half of the water molecules will remain here. But here we have, for example, 2 kinds of ions. So how do we find the weight of 2 kinds of ions? Here it is not like only water molecule is there, and even in other cases like FeCl3, there will be 3 Cl minus ions and 1 Fe3 plus ion. So how do we find the molecular mass to calculate the things in those cases? So what we use is conservation of charge. Because of conservation of charge, we will see that the entire thing has to be neutral. So the positive charge has to be equal to the negative charge. So like we say in case of NaCl, wherever there will be one Na plus ion, there has to be one Cl minus ion. They can't remain without each other, even if they are separate in the solution, like they are not bonded or anything, but still when they are together in a system, they have to remain together. So like I was saying, if NaCl solution, we pour half of it into another beaker. So in this beaker also, in the new beaker, there will be always the equal number of Na plus and equal number of Cl minus, and in the original beaker also there will be equal number of Na plus, equal number of Cl minus. So like when we are finding the mole, so since they are equal, so the number of moles of Na plus will always be equal to the number of moles of Cl minus. So the number of mole of 1 mole of substance we can find by, we can add the mass of Na plus ion, 1 mole Na plus ion and 1 mole Cl minus ion will give 1 mole NaCl, because always 1 and 1 will remain there. So we can, like we saw, mass of 1 mole of Na plus, mass of 1 mole of Na minus will be mass of 1 mole of NaCl. So this NaCl, although it is not actually a distinct molecule, we can consider this formula as a unit. So the molar mass of Na plus and the molar mass of Cl minus, it will in any case give the mass which is of 1 mole of NaCl. So we call it gram formula mass and not molecular mass, because no molecules are present here. And even when we talking about a solution, if we take a drop from one solution, one drop, like in that drop also the number of Na plus and the number of Cl minus will always be equal. So we can, that is like if we have x Na plus, there will always be x Cl minus, so there will be x NaCl. So just we can expect that in terms of gram formula mass, that is the number of Na and Cl together present. And now we come to a little bit complicated thing, which is called the equivalent weight. Because it is a little bit complicated, because it is a defined concept. By what defined concept I mean, like in molecular mass, it is mass of a molecule. We can physically see, not see, we can understand a molecule. Molecule, it has a mass, it is molecular mass. But this equivalent thing, it doesn't actually exist in reality. We have almost invented it to make calculations easier in equations regarding chemical reactions. So let us understand what is it. So like any reaction, we have A plus B equal to product. Now this A and B, it will depend on the stoichiometry of the reaction. So there might be x mole of A, y mole of B. But we define the thing equivalent as such a way that always one equivalent of A reacts with one equivalent of B, no matter what the moles. So we have to define the equivalent weight, and that is why it can be understood that it will depend on the reaction. For different reactions, if A is the same molecule, in one reaction it can have different equivalent weight, in another reaction it can have different equivalent weight. If the B is different or the nature of the reaction is different, because as I said, we define what is equivalent, and we define what is equivalent with respect to always that each, not only case of A and B, if there are 3 reactant, 4 reactant, every reactant should react one equivalent with one equivalent of each of the other reactants. So we need to understand this with examples. For examples, we first see acid. Like in the book, it will be written that equivalent weight is the weight that it is something like which reacts with 1 part of hydrogen or 1/12 of part of carbon, like that. So okay, I think I missed one thing. Here when we are talking about mass of nucleons, you will see that in the definition in the books, it is always written 1/12 of mass of carbon. So what is this 1/12 of mass of carbon? We are talking about nucleons, this proton or neutron. So here if we see the mass number of carbon is 12. So a combination of neutrons and protons there is 12. So if we 1/12 that, we get the average mass of 1 proton and 1 neutron, which is equal to this thing. So when we say relative to 1/12 the mass of carbon, we are what we mean to say is relative of 1 AMU. So the mass of carbon is 12 AMU, and 1/12 of that will give 1 AMU. Yes, so coming back to this, again it was, as we were telling, it was defined as which reacts with 1 part hydrogen or 1/12 part carbon. So what is this 1 part hydrogen? As I said earlier, this A and B. So in that case, they are assuming this A or this B is hydrogen, and because hydrogen's valency is 1, one equivalent of hydrogen is equal to 1 mole of hydrogen. That is why they hold this as hydrogen, and this will be what we are finding out. So that is how they calculate the equivalent weight which is relative to hydrogen, because hydrogen has the least, is the smallest valency. So if we find it with respect to hydrogen, there will be no problem in the future, because all other elements have higher valency or equal to 1. So there will be no fractional number of equivalents. So number of equivalents will always remain whole number. So now we see acid base reaction, and if in the books we see equivalent weight of acid is always in molecular weight of acid by basicity of acid. So why is it? First, I hope you know what is the meaning of basicity. Basicity of an acid is the number of protons which are produced when the acid is dissolved in water or during the reaction. So here we have H2SO4. So 1 mole produces 2H plus, or 1 molecule produces 2H plus, or 1 mole produces 2 moles of H plus. And we take sodium hydroxide. Here we take 1 molecule of sodium, not molecule, I mean formula. We can think of it as 1 unit, so we can call it 1 molecule. So we see that 1 OH reacts with 1 OH, 1 H plus. It will always be the case. But here we see that 1 molecule of H2SO4 gives 2H plus. So you see 1 molecule of NaOH essentially is reacting with half of a molecule of H2SO4. Again, in reality there is no such thing as half, because SO4 2 minus is a single thing, it cannot be half. But to define the equivalent, we are using this logic that a 1 molecule of NaOH reacts with half of the molecule of H2SO4. So we see if 1 molecule of NaOH reacts, 1 mole of NaOH reacts, it will require 0.5 mole of H2SO4 to react with it. Now we see this one produces only 1 mole only. 1 mole will producing 1 reacting unit. We can call it a reacting unit. So this reacting unit itself is the equivalent. So 1 mole equals 1 equivalent. And here also 1 reacting unit is 1 H plus. So it is 1 equivalent. However, we get it from half mole of H2SO4. So it is 0.5 moles. So when we do it separately for NaOH and for H2SO4, we see 1 equivalent equal to 1 mole. Here 1 equivalent equal to 0.5 mole. And weight of 1 equivalent will be equal to weight of mole. And we know weight of 1 mole is the gram molecular mass or the molar mass, which is here the formal mass. So equivalent weight we can get it equal to the molar weight. But here 1 equivalent corresponds to 0.5 mole. So weight of 1 equivalent will be weight of 0.5 mole. And thus the equivalent weight will be 0.5 into the molar weight. So it is molar mass by 2. And here we see this equation is exactly this equation, which is molecular weight of acid by the basicity of acid. So that is why you can understand that because it dissociates into 2, so here we have the one which is the reacting unit, which corresponds to half of the molecule of H2SO4. So that is why we have to divide it by 2. And similarly, in case of base and an acid, it is molecular weight of base by acidity of base. Acidity referring to the number of OH minus produced when the base is reacting or when it is dissolved in water. So here we see CaOH2. So 1 mole will again give 2 reacting units. So if we hold 1 reacting unit as the equivalent, so it will correspond to 0.5 mole. So again similarly 1 equivalent is 0.5 mole, and weight of 1 equivalent is weight of 0.5 mole. So half of the molar weight or the molar mass by 2. And again here 1 molecule gives 1 reacting unit. So again it will be 1 equivalent equal to 1 mole. So again the equivalent weight will be equal to the molecular weight. Now for here only there might be one question that what happens if like calcium hydroxide is reacting with H2SO4. Here also one molecule give 2H plus, here also one molecule give 2OH minus. So according to convention we have to give it by this formula only, that is we have to divide both by 2, but we will see a little later that in some types of that it is important to follow it because of convention, but actually it doesn't change the result that much. So here we have taken the case of salt. For a salt, it is formal weight of salt and charge on each cation and the number of cations. For example, here is Na2, so there are 2 Na, so each has 1 plus, so 1 into number of cations 2, so here it will be 2. And if there are like 2 calcium ions, so it will be 2 into 2, 4. And here also one question can be there, that why it is only the weight of, or charge of cations and not that of anions. But the thing is, if we look carefully, for a salt, total charge on cation will be equal to total charge of anion. So this one will also do just fine. But because of convention, we will take that on as the cation only, because here see, here it will come 1 into 2 equal to 2. If we take total charge of anion also, this is also 2, so it will come the same thing only. So here we take a reaction, it reacts with HCl to give water, carbon dioxide and NaCl, and here we see similarly HCl, it gives one reacting unit which is the H plus, so it is 1 equivalent equal to 1 mole. And similarly this, and equivalent weight is equal to the formal weight. And here again we see for 1 equivalent of Na plus, we will take half a mole of sodium carbonate. So again this will become 0.5 and molar mass by 2. So I noticed my screen was masking the writings here, so if you want to see it again, you can see it. You can also take a screenshot if you want, or write down, pause the video and write down something. I'm just showing the slides again because my screen was covering a part of the slide. So I noticed that my screen was covering this part, so it is nothing, it is I have just written the 0.5 by divided by 2, which actually becomes the same as divided by acidity of base, or by basicity of acid. So now we come to redox reactions. It is a little complicated. So in redox reaction we have transfer of electrons. So as we are talking about equivalents, which is the reacting unit, here electrons are the reacting unit. So here when we say one equivalent will react with one equivalent, here we have a reaction between KMnO4 and oxalic acid, which is a redox reaction. So here this one is actually getting reduced, which means there is 5 electrons transferred to KMnO4, and this one is getting oxidized, so 2 electrons are being removed out of this. So here when we talk about equivalents here is one which transfers 1 electron. So this one we have to divide by 5 so that it transfers 1 electron, and this one by 2 so that it transfers 1 electron. And that is what this formula is: molecular weight of reagent by number of electrons transferred to like reduce or oxidize one molecule of reagent. And one important thing here is it will depend on the reaction, like here it is KMnO4 to MnSO4, here 5 electrons are transferred. So there can also be like KMnO4 to MnO2 for their 5 electrons will not be transferred. There I think 3 electrons will be transferred. So like just seeing K-4, we shouldn't directly do it divided by 5, because the reaction can be different. And so the change in the oxidation state, it depends on that. So now, as I said, it is invented, this equivalent thing. So why was it invented? We will see there is a thing called normality. Normality is number of gram equivalents, which is the number of equivalents of solute in the solution divided by the volume of solution entered. And this gram equivalent is again the same thing as gram molecular mass, so which is given in gram per equivalent. Like gram molecular mass was gram per mole, which is the mass of 1 mole of that thing, and gram equivalent is gram per equivalent, which is the mass in grams of the equivalent of that thing. So the normality, if we have any titration or like any reaction in solution, we can use this normality as N1 and N2, and this V1 and V2 being volume of solution. Like we are reacting acid and a base, like we have volume V1 of acid, and that concentration in normality is N1. It is reacting with volume N2 of base, with concentration N2 of base in volume V2, and if we react it, for complete reaction there will always be N1 V1 equal to N2 V2. It is also called the normality equation, and it is essentially used in any kind of titration. And the advantage is in any kind of titration and any kind of whatever will be the chemical equation, regardless of the stoichiometry, if we find out the concentration in normality using the equivalent weights, it will always follow this equation. So that is the end of this video. So thank you, and if you found it helpful, you can like, share and subscribe, and let me know in the comments if you would want some solving of some questions, maybe from competitive exams or from any books, so we can do a video on that also. So let me know that in the comments, and thank you.